Hello, and welcome to this webinar brought to you by Xidas and PowerFilm. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's session. Just to the right of the main presentation window is the speaker bio window with background information on today's presenters. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed into the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenters. With us today is Saurabh Dhillon, the co-founder and director of business development for Xidas, and Dr. Dan Steeler, the president of PowerFilm. To read more about the presenters, please look at the speaker bio window right next to the main presentation window. Guys, welcome to today's event. And with that, I will pass things along to you to get started. Please go ahead.
Hi, everybody. My name is Saurabh Dhillon. I will be starting off the webinar with everyone and talking about a couple of things, starting off with why energy harvesting, why look at energy harvesting specifically for the wireless Internet of Things marketplace that's continuing to emerge. And then I'll be focusing on the vibration-based energy harvesting application and the benefits and values that can offer to the table. And then I'll turn it over to Dan, who will talk about solar and that application when it comes to energy harvesting for electronic devices. So that being said, getting started, wanted to set the stage and talk a little bit about wireless IoT in general first, which I'm sure many of you have already heard of and understood to some level, and that's the concept of connecting billions and billions of sensors throughout society in a variety of different places, collecting a ton of different pieces of data and information, and using that information to make a much more efficient society. Now, whether this is, smart agriculture or smart factories or you name it, whatever the application might be, smart cities, making something smart, there's a massive value of going wireless and having these sensors that are collecting the data be wireless. And the reason for that is now you don't need to worry about connecting these sensors and placing these sensors near some sort of electrical infrastructure where it needs to be plugged into a wall or you need to provide it power. If you make it wireless, now you have the flexibility, ease of implementation to place these sensors anywhere you want and in previously inaccessible locations. So for the smart agriculture application, for example, there's no way you're going to be able to wire power to a bunch of sensors that, let's say, you want to put into a field. So going wireless is really the major drive for sensors when it comes to Internet of Things applications. And that runs the span of all the way to factories and cities and anywhere. Wireless is the way to go. Now, the problem with wireless is, we have had wireless sensors exist now for quite some time. The reason why a lot of applications have been slow to implement is because the issues and limitations associated with wireless sensors, particularly what you see there, number one, which is batteries. Because if it's going to be wireless, they're typically going to be powered by batteries. Now, there are other huge issues associated with wireless sensors like bandwidth, data bandwidth issues and cybersecurity, which is something to note here. But really what we're going to discuss in this presentation is that number one pain point, which is batteries. Now, I won't spend too much time on the next couple of slides, but just to give, again, a quick overview of a conventional wireless IoT system, there's three components to it. One is the actual sensor that's monitoring the sensors, and because these are wireless now, they'll be using some communications infrastructure, whether that's Bluetooth, Wi-Fi, cellular, LoRa has become quite popular. This infrastructure is responsible for taking that data from that sensor and sending it to the cloud. And then typically that cloud is where all the analytics is done, the artificial intelligence sometimes, and then where the applications are where you can look at the data. This is important to note because the typical architecture of a wireless sensor is collect a bunch of raw data, send it over this wireless protocol to the cloud where then the computing is being done. And because of that, and because you're sending a bunch of raw data, and you have to be talking to the cloud all the time, there's a high power consumption that's going on with the sensor, particularly every single time you're transmitting. There's a high power consumption happening at that sensor. So oftentimes, what people will look at is the communication side of things, and how do we find a very low power consuming protocol like a Bluetooth or a LoRa as opposed to a Wi-Fi in order to reduce the power consumption of our sensor. But there are other methods like using edge computing to reduce the operating power of the sensor to increase the battery life as well. And then the third, which I'll talk about later as well, is leveraging energy harvesting, such as ourselves, to increase the power availability, the power that's available to the sensor to consume. So some key aspects of a wireless sensor to note is, again, it does need to be wireless. It's important for it to be small. It's important for it to be cheap. And it's important for it to be smart. Now, number 2 and number 3 are quite important, mainly because it allows you to, for number 2, it allows you to put it in a lot of different places. And number 3, it allows you to put a lot of sensors everywhere. So the more sensors you can place in an environment, the better. Now, the problem with it being wireless, as I had mentioned, typical wireless sensors are lasting only about 1 to 2 years, and oftentimes less than that, depending on their duty cycles, how often they're taking a measurement, how often they're transmitting. So this ends up becoming a massive maintenance headache. If I look at, let's say, a factory, for example, and I want to take the application of machine condition monitoring, where I want to monitor the condition of my machinery, my compressors, my pumps, my motors, and let's say I got hundreds of sensors throughout my equipment in a factory. This becomes a maintenance headache to have to replace these batteries once a year. And it's not just the cost, and you can see an estimated cost right there with how much it costs to replace a battery. And it's not as simple as, replacing your smoke detector at home. You got to send someone out, which is labor, to go and replace the battery and then recommission the sensor. So there is a legit expense to it when it comes to industrial applications. But the headache itself is not even worth it. So these batteries are not all dying at the same time. These sensors are not dying all at the same time. So you end up you're just constantly replacing batteries. And that is a massive headache and limitation for many industrial companies. The reason why they don't even look at wireless sensors or the new age of predictive maintenance. Let's say they haven't even 80% of companies have looked at predictive maintenance solutions. Only 20% have really started implementing things, and a massive reason for that is the headache of dealing with these battery replacements. So how do we increase that battery lifetime? You reduce that major pain point. Now, there's a clean tech issue as well that I'd like to mention, which is with billions and billions of sensors eventually that IoT promises to implement in society, that's a lot of batteries that we're going to have to dispose of, and that has a massive negative impact on our environment as well. So energy harvesting is not just practical, but it's an efficient solution for the environment as well. So the bottom line becomes, how do we increase the lifetime of our wireless devices? And there's really 2 major approaches here. One is by generating power from the ambient environment, and that's energy harvesting. And I'm going to talk to you about a couple of forms, focusing on vibration and then focusing on solar. But there is another approach, which is reducing the actual power consumption of that wireless device. And by introducing intelligence to that sensor, you are able to do this. And with a combination of energy harvesting with this, the goal is to get that wireless sensor, let's say, to a battery life of 10 plus years, a lifetime of 10 plus years. And that's when the application truly becomes fit and forget. And that's what you want. You want to install your sensor and completely forget about it. Here at Xidas, we do work in both. So many of you may know us as just a vibration energy harvesting company. We are a National Science Foundation partner, and that first phase was developing those energy harvesting solutions, which I'll talk about. But the second phase of our development has been developing autonomous sensors with onboard AI and intelligence, which will be launching next quarter. So I'll touch upon that as well, because it is a great pairing with the energy harvesting. So to talk about energy harvesting, there's really three aspects to a complete system that you need to know about, and each one is very important. So oftentimes, let's say you may know about if we're looking at solar, you might be familiar with the photovoltaic cell, the actual solar cell, but there's other aspects of the energy harvesting system that you need to implement in your system in order to leverage energy harvesting. The first, of course, is the generator, and this is the actual mechanism that's capturing energy from the environment and converting it into an electrical signal. So it's, solar cells for photovoltaic, thermal have their gradients, RF got their antennas, the types of antennas I'll talk about, and then vibrations got a couple of different principles as well of how to convert that physical energy that's in the environment into electrical energy. But now the job's not done. You do need something called a PMIC, which is a circuit that now takes that power that's coming from the generator and conditions it so that it's appropriate for an electronic system or for charging up a battery. Now, you can directly, with the power generated, power up an electrical system from a PMIC, but it is highly recommended that you still have battery storage, energy storage in your system as well. And what you're doing is you're taking your energy harvester and you're trickle charging a rechargeable battery. And the reason for that is because the energy in the environment is not always available. So for solar, for example, during the night, you're not going to have any sunlight available. You still want to power your device. Same with vibration. Let's say I'm capturing vibrations off of a machine, and the machine turns off. There goes your power source, and you still want to power your system. So these are the three aspects that are all important. I'm going to focus I'm going to touch on the two other types of generators, energy harvesting generators, and then focus on vibration moving forward. So with thermal, this is a fantastic mechanism to use. This company Matrix, for example, they make a great thermal energy harvesting generator. Now, the way this works is you need a temperature gradient in your application in order to generate any sort of amount of energy. And you can generate a good amount of energy. So as you can see over there, we're talking milliwatts of power, which is fantastic and totally appropriate for a wireless sensor. The issue with thermal is, and why it may not be a highly utilized source of a highly utilized energy harvesting solution, is there are not that many locations or applications that have this temperature gradient for you to use. So it's not a readily available energy source in the environment. Now, directed over the air is another popular energy harvesting mechanism that's been increasing in popularity over the past few years. It's the use of having a transmitter that is plugged into the wall and shooting energy to your wireless sensor that has a receiving antenna via infrared or via RF. Now, there are still some practical issues associated with this sort of energy harvesting technique, which is why the adoption is still slow in the industry. And the one is due to the practicality of it. You still need outlets somewhat nearby your wireless sensors, and the range that you get is from that transmitter is still it's not there just yet. When you're looking at RF, you're only looking at less than 10 feet away. Infrared is better, 10 meters away, but infrared requires line of sight. So if it's behind a pillar or a tree's in the way for an outdoor application, let's say, the signal's not going to get there. So again, this is appropriate for a lot of different applications, but not every application. Which leads us to vibration and thus solar as well. I'd say that solar is going to be the most popular approach for energy harvesting, and the reason for that is light typically is everywhere and the easiest to harness. The reason why vibration becomes at a number 2 is particularly when we're looking at industrial applications. And the reason for that is a lot of these factories that, let's say, you want to monitor the equipment of, are typically very dimly lit, which means you can use indoor solar cells, and Dan will talk about that. But at the low luxes, you will generate power, but it might not be enough for your wireless sensor, and it depends, of course, on the wireless sensor that you're using. However, what is prevalent and a lot closer to that sensor in regards to energy available is the vibrations that are coming off of that machine. And that's where vibration energy harvesting becomes incredibly practical and useful for your wireless sensing solution. Now, the problem has been to date, and I'm sure there's a lot of wireless sensor engineers out there, or condition monitoring, predictive maintenance engineers that have looked at vibration energy harvesting to increase lifetimes of their wireless vibration sensors. The problem that you've probably seen in the marketplace up until now is that there hasn't been a practical energy harvesting solution for those sensors, and the reason is this. Machines, motors, pumps, compressors, they vibrate at very, very low vibration profiles. They vibrate at sub 100 hertz frequencies. They vibrate at sub 0.5 G accelerations, oftentimes 0.1 G accelerations. They're barely humming. It's going And so it's tough to get a significant amount of power from that very, very low vibration profile. Now, the piezoelectronic vibration energy harvesters out there that I'm sure a lot of people are familiar with, they do not generate a good amount of power from this vibration profile. I'm talking about getting at least 1 milliwatt of power out of that vibration profile. They're not gonna be able to do that. Piezoelectrics is much better for higher frequencies. So there's applications absolutely for them, but when it comes to machines, not necessarily. And now conventional electromagnetic vibration energy harvesting, which is the use of a magnet and coils type approach system, they generate a good amount of power. Oftentimes 10 milliwatts plus, even more depending on the size of it. But up until now, they have been quite expensive. So they could be used for maybe some train applications, some specialized applications. But an industrial IoT application where you're going to put hundreds of these on all your sensors in a factory, $500+ is way too much for that solution to be practical. So it was this chicken and the egg scenario that actually led to us getting funding from the National Science Foundation to bridge that gap. And that's exactly what we did with our vibration and based energy harvester, which you can see right here. This is the generator. So you still need a PMIC and you still need a battery, of course, as I mentioned earlier. This is to give you a size comparison of it next to a typical D-cell battery. So it's quite small, a little fatter. And what we developed was, this is an electromagnetic based energy harvester that's small, as you can see there. Produces significant amounts of power, as you see in regards to the power generated right there. And I'll talk about that in a little bit more detail. But it's also low cost. So we've got a patented design and manufacturing patents on the way we build this. Allows us to sell this for under $40, $35 in single quantities, and then goes down vastly as you increase your quantities there. And so now this becomes actually a practical solution for industrial IoT. Now, there's no getting away with the one caveat with vibration energy harvesting, no matter what the solution is, which is it does need to target a specific frequency, a specific resonant frequency. Here you can see the data we're showing for a 60 hertz version. And as you can see, depending on the amplitude, the acceleration of the vibration, that's how much power you're making. So if the machine's vibrating quite violently at, let's say, a 0.7 G acceleration, you can get up to 45 milliwatts of power from this generator. But realistically speaking, you're down to the the 0.3 Gs type of or 0.2 G type of profile, and that's where you're gonna see a more realistic power output of 5 milliwatts. Now we have versions tuned for 20, 30, 50, 60, 70 hertz. So depending on what your application is vibrating at, you do need to know that and then buy the energy harvesting solution based on that. So I'm going to breeze through this, but a bit obvious. Some of the applications here are pretty much anything that's vibrating: machines for predictive maintenance, sensors, train condition monitoring, bridges, construction equipment, pipelines, all great applications. We do have a PMIC that we offer as well. This is a little bit above and beyond a PMIC, because if you buy a PMIC, let's say from another company, there's still a lot of engineering work that you've got to do now to integrate that PMIC with your wireless sensor and with your system. A lot of additional components that you need to add and do certain configuration on settings. This PMIC is universal, so we've done all that for you. So this becomes a drop-in solution. It comes with overcharge, discharge protection. It allows you to select DC or AC inputs, so you can use this with solar, you can use this with vibration or thermal or RF, whatever your energy harvesting is. And it's got fuel gauge in here as well, so you can see the level of battery, of energy storage that you've got when taking in your battery. And I have this here for reference in case someone wants to look at the specs. Of course, you can reach out to me after as well. And then finally, that last piece of the puzzle I had mentioned, which is that energy storage, we offer a rechargeable battery as well. So you have all the pieces of the puzzle in order to take vibration energy harvesting and have the full solution. The value of this battery here is oftentimes customers are going to use super caps for energy harvesting, because when it comes to rechargeable, secondary batteries, lithium is not very good for wireless transmission. They cannot handle high current pulses. Super caps can, so you want to use super caps. However, super caps can be quite leaky, whereas lithium is very good in that standpoint. So this battery is something we've partnered with the Hong Kong Polytechnic to introduce. It combines both. It's a hybrid, a super cap lithium battery. So it's perfect. It's ideal for energy harvesting. It's got great temperature range as well for industrial applications. As you would imagine, we do combine now all three of these components into one standalone unit. So it's an all-in-one plug-and-play product that you can mount this on your machine. And it's an IP67 enclosed device, and you can plug your wireless sensor directly to it. And this is your quote-unquote endless source of power. However, the best approach I would recommend for people that want to evaluate energy harvesting for the solutions would be this educational development kit. It's a lot more flexible, easier to configure. It comes with our vibration energy harvesting generator, as well as a indoor solar cell from PowerFilm. You can use both of those with this product and play it around with different applications. We sell this online as well right now, along with the VP3. And yeah, so this is what I would recommend for getting started with energy harvesting and seeing how it would work with your system. As you can see here, it comes with the rechargeable battery, and it comes with the PMIC on that circuit. I won't talk too much about this. Keep the topic focused on energy harvesting and pass the ball to Dan here in a second. But at Xidas, we are introducing something next quarter, as I mentioned, called eChips. These are fusion sensors that are completely autonomous, so they don't rely on the cloud at all, or they don't need any cloud connectivity at all. They've got the intelligence to take measurements and data log, and then compare those measurements on board with a variety of different models. So it does onboard conditioning, calibrating, filtering, processing, and then it will compare the data it collects with various different thresholds and models. It's got onboard AI where it can actually learn right on that sensor, so not in the cloud. It's learning right on that sensor what a healthy model is, what an abnormal model is, and then can save that model and use that as a way to generate a variety of different alarms. And then only when an alarm is triggered does it actually ping the cloud, or only if you want to report once a day or once an hour. This dramatically increases the lifetime in regards to the sensor. Just regular battery power, these are 5+ years without energy harvesting. With energy harvesting, and I'm talking about Wi-Fi, which is a very power-consuming, high power consumption protocol. It's 10+ years. Here are some of the MVP products we'll be introducing. Vibration, environmental are the first two. But yeah, that's my slides. I'm going to hand over the mic to Dan to talk about the solar application.
All right, thanks, Saurabh. Hi, my name's Dan Steeler from PowerFilm Incorporated. Just a quick brief. PowerFilm manufactures solar modules for applications from microwatts to kilowatts using amorphous silicon, crystalline silicon, or gallium arsenide solar modules. Today I'm here to talk with you a little bit about energy harvesting with solar. So the first thing I'd like to talk a little bit about is the amount of power available in different environments. On the left side of this slide is a picture of our LL200-3-37 solar panel. Its dimensions are about 1.5 inches by 4.3 inches. Using that panel, the table on the right lays out some possible scenarios for powering a Bluetooth low energy system. In outdoor light at 25,000 to 100,000 lux, a Bluetooth low energy gateway can be powered. In typical indoor lighting from 200 to 1,000 lux, Bluetooth low energy sensor modules can operate with faster or slower update times depending on the amount of light available. And then finally, in very low light levels, around 50 lux, a BLE or Bluetooth low energy beacon could still be operated. And you can kind of see in the table, get an idea of different locations: direct sunlight, shading outdoors, near a window, on a desk, under a desk, give you an idea of what a place in a room may be or look like in your application. The second thing to consider with regard to power consumption is the type of sensor that's going to be used in your application. Different sensors consume different amounts of power depending on the sensing technology. So on this slide, I'm going to provide some general ideas. Generally speaking, sensors like temperature, humidity, Bluetooth low energy beacons, and light meters are very low power and operate in dim indoor environments, less than a few hundred lux. The next tier of sensors operate indoors but need a little extra power. Something like a inertial or force or acoustic sensor would work well, especially in a little bit brighter environment, something like a store or an office space that's brighter, like 1,000 lux. And finally, there are some items that require a great deal more power, like 50,000 to 100,000 lux, that would do well in outdoor environments. Examples of these higher power systems would be cameras, displays, or lights. When adding solar energy harvesting to your system, there's a few things to consider early on in the design process, or a few questions to ask. First, take some time to quantify the lighting scenario that your device will see. Is it outdoors or indoors? If it's indoors, what is the average illumination? 200, 400, or 1,000 lux? How much light can you expect per day? Is it in a building that operates with its lights on for 10 hours or 12 hours per day? Is it outdoors? If it's outdoors, you can use something like NREL's PD watts calculator, which is available on the web. It provides information about outdoor environments or outdoor illumination for each month of the year in any specific location. The next question is, does the device need to operate for 24/7, or is it only need to operate when illumination is present? Answering those questions will give you an estimate of the amount of solar power available for your application, and you can use that light availability to make a rough guess on how much solar you will actually need for your prototype. From there, think about the type of light your application will use. Is it the sun, an LED, a fluorescent light? If it's the sun, there are many solar technologies to choose from. If it's a high-efficiency indoor light, like an LED or fluorescent, there are fewer technologies that will work effectively. Look to something like amorphous silicon solar, specifically optimized for indoor lighting if you have a application that's specifically looking at the indoor high-efficiency lights. The next question is, what type of durability is required? Do you need to be able to withstand years of UV exposure? Will the device be located in an extremely high humidity environment or frequently washed down with water or other chemicals? Answering these questions will help you choose the type of encapsulation required for your solar module. Now let's talk about what solar efficiency tells us and what it doesn't. Solar efficiency does not adequately represent how much power a panel will produce in all lighting scenarios. Efficiency is measured under a very specific set of parameters: 1,000 watts per meter squared illumination, 25 C for the temperature, and AM 1.5 solar spectrum. Since high-efficiency indoor lighting such as LEDs or fluorescent lights produce light almost exclusively in the visible spectrum, they are quite different from sunlight, as we will see in a moment. The second factor when thinking about how a given technology could be predicted to perform indoors is how the quantum efficiency of that cell will affect its performance. The quantum efficiency of a solar cell will show you how capable it is of absorbing a specific wavelength of light. When it comes to something like a multi-junction cell, it's important to look at their quantum efficiency and determine if all junctions will be able to get the light they need absorbed from the light source. An example would be a 3-junction gallium arsenide cell that's 30% efficient outdoors and has one junction that's specifically focused on absorption of infrared light only. This means if it's paired with a visual spectrum light source, its performance will be very low because the power output of the cell will be limited by the fact the bottom junction or diode has no infrared light to absorb. Finally, the last factor is parasitic leakage. Some solar technologies, such as CIGS, tend to have a significant amount of leakage. This is not a problem outdoors in high-intensity light because the current production is much higher than the leakage. But indoors where light intensity and current production is low, leakage can render a cell totally unusable. Technologies such as amorphous silicon inherently have lower leakage, making them an ideal choice for indoor solar energy harvesting. Now let's look at the differences between indoor and outdoor light. The plot on the left shows the spectrum of sunlight after it has been filtered by the Earth's atmosphere, yielding what's called the AM 1.5 solar spectrum. It's much broader than the spectra on the right, which show a few types of indoor lighting. With the exception of the incandescent lighting, the indoor lighting is primarily confined to the visual spectrum, as you would expect from a high-efficiency type light. Since the efficiency of solar material is the measure of how completely a solar cell is able to use the entire light spectrum, you'll want to choose a solar technology that's well matched to the visual spectrum with a low parasitic loss to optimize your indoor power production. An interesting thing to note is the black curve in the right plot. This is the lux meter response. The lux measurement only focuses on the center of the visible spectrum rather than being a full spectrum optical power measurement. So the power produced by a solar module will not be the same for a given lux level of different light sources. This is especially true if a light source emits a great deal of infrared light. Lux itself was actually derived based on to match the response of a human eye, not to measure the power of a solar cell. All right, so now let's discuss the parasitic leakage a bit more. Solar cell recipes can be tailored to indoor lighting. This is done by managing the parasitic leakage and by tailoring the device's light absorption to match the high-efficiency indoor light sources. The plot on this slide shows that by managing the parasitic leakage of a device, the open circuit voltage at low light intensities can be increased by 30%. This increase in open circuit voltage will increase the overall power of the device at low light intensities. This increase in low light performance is done at a cost of high intensity light performance. So if an indoor light module is taken outdoors and measured at full sun, its output will be less than that of a cell that's optimized for outdoor use. Additionally, taking an indoor optimized cell outdoors long term will result in reduced performance due to the increased light degradation at higher light intensities. Let's compare the power density output of a few technologies. First, CIGS, which performs at a moderate efficiency outdoors, does not work indoors because of the parasitic leakage that is inherent to the technology. Next, the crystalline silicon performs reasonably well, but there's actually a large spread of performance for this technology. Typically, for small panels that would be used for indoor energy harvesting, performance would be lower because they need to be divided up into small cells and wired together, since this technology has a power point of only 0.5 volt per cell. Cutting the silicon solar into small cells induces parasitic leakage, and wiring them together creates additional area between cells that cannot absorb light. Both of these factors reduce their efficiency. That being said, crystalline silicon still has the best power production in incandescent lighting due to the availability of IR in that light. Amorphous silicon does well because it takes few cells to achieve a reasonable voltage for energy harvesting. The parasitic leakage can be managed, and the quantum efficiency is well matched to the indoor light sources, even in the tandem amorphous silicon cells. This gives the highest performance in the table for the high efficiency light sources. Multi-junction gallium arsenide does well with parasitic leakage and voltage, but falls down when matched with an indoor light source, since one of the junctions is dedicated to collecting infrared light, and there's little to be found in limiting the total output. The plots on this slide show how power generation of amorphous silicon compares to the measured lux level of light for both outdoor and indoor lighting. The left plot shows the performance of an outdoor optimized cell, and the right plot shows the performance of an indoor optimized cell. Look at the 400 lux point on each plot. The cells made with the indoor light recipe produce more power than the outdoor cells. Plots also give you an idea of how much power you could expect at different light levels for each type of cell and in different locations. One thing to note is even when within a given room, light levels can change significantly based on the distance from a light source. For example, if a panel is mounted vertically on a wall, you could see up to a 3x difference in illumination based on the beam angle of the luminaires in the room, depending on the height at which the cell was mounted on the wall. Also, a window can easily change illumination in a room by a factor of 10 during the day. When starting a new solar energy harvesting design, the first step is to understand the power consumption of your device. Next, look at the lighting scenario for the typical use case. With this information, you can start to estimate the panel size needed for an initial prototype to prove the concept. These two pieces of information will allow you to determine the type and size of storage element you need to ensure that you can achieve the desired system uptime. Keep in mind that batteries and capacitors both have a self-discharge that is proportional to the size of the storage element. So including a very large battery into your energy harvesting system can have a negative effect, since its self-discharge will need to be included in your power budget. Next, define the physical parameters that are important for your application. Does it need to be a certain thickness, conform to a surface, be UV resistant or waterproof? How can the panel be best mounted into your device? Does it need to have wires? Would you rather use a PCB connector? Or is conductive epoxy mounting the right solution? Finally, check that the cost at your anticipated volume will meet the market requirements of your application. Do your customers value the reduction in maintenance costs, battery waste, and increased uptime? When it comes to mounting panels, there are a number of options available. Solar in general is not compatible with the standard reflow process. However, there are a number of other options. PowerFilm solar's modules can be made with front side contacts to solder directly to a PCB or folded through a PCB slot and soldered. Panels are also available with backside contacts that can be electrically connected to a printed circuit board using a conductive epoxy. PowerFilm's flexible solar panels pair well with both flexible and standard FR4 printed circuit boards. Finally, PowerFilm has a line of panels that are compatible with flexible printed circuit board connectors. These are the types of connectors that you would see flexible circuits connecting into a board. So say if you had a pouch-type lithium-ion battery with a polyimide copper connector, and you're trying to plug that into your circuit board, it would use this similar type of flexible printed circuit board connector, which is shown in the bottom right corner of this slide. These connectors can be installed using a standard reflow process, and the panel then can easily be slid into the connector to power the device. PowerFilm has a proven track record of high-quality custom designs across multiple industries and technologies. You can be confident we can provide a solution that meets or exceeds your requirements. With over 200 years of combined engineering experience in solar product development, our team's here to help you with your solar integration project. No matter what your application is, we have the knowledge, experience, and capability to meet your IoT and remote power needs. We offer many standard electronic component panel sizes to get you prototyping and can make custom designs to fit your exact application. PowerFilm's blog offers a wealth of information on solar, and we have other useful tools such as a build-your-own panel calculator on our website. So go ahead and buy a development kit to jumpstart your energy harvesting design today, and then please contact us if you have an interest in solar energy harvesting. We'd love to help you create a sustainable, low-cost, low-maintenance device with the help of solar. Okay, now we're going to take a few questions. Matt, what's our first question?
Yes, indeed. Thank you. And thanks, guys, for that great presentation. So we're going to move into the Q&A now. If you guys haven't submitted your question yet, you can do so now by entering it in the Q&A box on your screen. So just enter your question and then hit submit, and we will try to answer it before the close of the session. Okay, now for our first question from the audience. Do you work on energy harvesting from vibrations induced by steps or walking? Guys?
Yeah, thanks for the question. It's a good question. So the short answer is a no, and the reason being that those frequencies are typically under 10 hertz. They're very low frequencies, and so the design of the product needs to be completely different. It's less of a vibration and more of a motion. So our vibration energy harvesters are more targeted for machinery. The lowest frequency we could probably hit is 10 hertz. We could probably do a custom 10 hertz or 15 hertz. But what our comfort zone is typically 20 hertz up to about 100 hertz. Any frequency in that range is their sweet spot, and we'll be able to generate a good amount of power, being 1 to 2 milliwatts plus.
Excellent. Thank you for that. And moving on to the next question from the audience. The question reads, any plans to make them smaller? And the question was sent in, I believe, towards the end of Saurabh's prepared presentation. So the question is, any plans to make them smaller?
Yeah, another good question. So, yeah, the answer is yes. So actually, as the background of Xidas, we are actually a miniaturization company, electromechanical miniaturization company that is based off about 15 years of research and $20 million from the University of California, Irvine. So funny enough, the very first products we developed actually for vibration energy harvesting were so small you could embed them inside of the printed circuit board. So you could actually have an array of these really small electromagnetic energy harvesters right inside the printed circuit board. The reason we went off that path and developed something a little bigger was so that we could actually hit the power requirements of wireless sensors, which back in the 2-3 years ago was more in the average of 1 to 2 milliwatts of power. Now they're consuming a lot less power, and so yeah, we do have in the pipeline plans to go smaller and even go back to the printed circuit board approach and embedding them inside of the printed circuit board approach. But as of right now, the near future pipeline is those intelligent sensors I was touching upon.
Great, thank you for that. And I'd like to just take a moment and answer a few questions that came in from the audience. The questions were whether or not the replay will be available. Yes, it will be. So this entire webinar, including the Q&A session, will be available for replay approximately 1 hour after the live event ends, so you can come back and watch this again. Thank you very much for your interest. Okay, moving back to the questions. Okay, next question from the audience. What vibration frequencies and amplitudes can I capture energy from?
Yeah, another great question. The answer is pretty much any, all the way from really high frequencies and impulses to low like motion level, and then based on the type of frequency you're trying to capture from, you select the appropriate technology. So if you're going for really high, 100 plus hertz frequencies, piezo becomes the technology you want to look at and evaluate. For anything lower in frequency, 100 hertz and lower, electromagnetic becomes the appropriate technology to look at. So that's the kind of the rule of thumb there. For us, we're like I had mentioned earlier, we're focusing in that 20 hertz to 100 hertz range, and that's because typical machinery is going to vibrate at those profiles. To give you an example, an AC or DC motor is typically, depending on the area, what country it's in, going to vibrate. An AC motor is going to vibrate around 50 hertz or 60 hertz. So that's the that's the target for one major target for our products.
Excellent, thank you for that. And I'd just like to remind the audience, we are now in the Q&A session. We have our experts from Xidas and PowerFilm online and ready to answer your question. You can still submit a question now by entering it in the Q&A box and clicking submit. Okay, next question. Should a standard or indoor panel be used in heavily shaded outdoor environments?
A good question. Typically, in a heavily shaded outdoor environment, you would likely still use an outdoor panel. Kind of the division point for us in deciding if it would be an indoor or an outdoor panel application is around the 6,000 to 8,000 lux range. If you're under the 6,000 lux, certainly you want to be using an indoor panel if it's consistently under that. If you're over the 8,000 lux, outdoor panel is always going to be the right choice. And then if you're kind of in that middle area, it can vary some, but usually there's a clear path one way or another. But typically it would be an outdoor panel even in a relatively shaded outdoor application.
Excellent, thank you for that. And moving along to the next audience question. How tightly can your flexible PV be wrapped?
So the bending radius of the flexible PV is really dependent on what we use for an encapsulation, and so the ultimate durability requirements of the application. But we can easily wrap down to less than a half inch, possibly less, depending on what kind of encapsulation we have to use on the product.
Excellent, thank you for that. Okay, moving along to the next question. I'm not familiar with this term, so I'm going to try to say it correctly. How does A-SI solar cells compare to organic solar cells in indoor performance?
Good question. That's something that gets asked very frequently, and so it's interesting right now when you look at the people producing the organic cells and then like the amorphous silicon we sell. The ultimate performance of the ones that I have seen that are actually commercially available are pretty similar. When you're looking at performance in the 500 lux-ish area, the differences will be in durability and lifetime. Typically, the amorphous silicon panels, if they're encapsulated for it to be a long life product, the lifetime will be over 10 years. In the organic products, your lifetime is somewhere between 3 and maybe at most 10 years. So it varies a little bit. The actual energy harvesting power performance is comparable in most cases, but the lifetime of the product may be slightly different.
Excellent, thank you for that. And again, I just want to remind the audience, we are in the Q&A session. You can submit your question now by entering it in the Q&A box and clicking submit. Okay, next question. what is the lifetime of solar harvesting parts and maintenance cost, including durability?
So that, again, depending on what the target lifetime is for the device, that helps us pick and choose what type of encapsulation you want. So if you wanted a long lifetime device, something that was 10 or 15 years, we would choose something like a ETFE encapsulation. We'd put around a border around the outside to make it totally waterproof, like IP67 rated. And with a system like that, the solar itself, it'll easily last 10, 15, maybe more years. Generally, with our processing, everything that we do for testing our encapsulants and our solar material and all the parts that go into our solar end product, we test to the IEC standard for solar, which is really a 20-year lifetime test for thin films. And so the encapsulations and the materials that go into it are all set to pass that 20-year lifetime test, as long as they're deployed appropriately.
Excellent. Thank you for that. And we have time for one or two more. So here's our next one. Might be the last one. Does PowerFilm currently offer solar panel for remote/standalone cold storage units?
Good question. I mean, I don't know exactly what that question's getting at, but I guess the short answer is we have solar panels of all sizes, from microwatts to kilowatts, things that you can fold up and pack away, foldable panels. We have semi-flexible crystalline silicon panels that have a high power density in a small package, and we have used those in the past to power things like standalone Ingo coolers, refrigeration systems, and that kind of stuff. So it's likely that we have a solution that will meet your needs, but we'd have to take a look at whatever type of cold storage system you're using.
Okay, thank you so much for that. And we are going to wrap things up right there. So guys, thank you so much for taking the time to be with us today and also taking the time to answer some questions from the audience. I'd like to also thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey, which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we'll talk with you soon.